In the probabilistic dance of countless particles, there exists a profound and statistical discipline known as statistical mechanics, a branch of physics that delves into the collective behavior of a large number of particles, unraveling the macroscopic properties that emerge from the microscopic realm. This narrative, woven with principles from probability theory, thermodynamics, and quantum mechanics, unveils the story of ensembles, fluctuations, entropy, and the statistical principles that govern the behavior of matter in diverse physical systems. Ensembles and probability distributions. At the heart of statistical mechanics lies the concept of ensembles, a collection of possible states that a system can occupy. Statistical ensembles, such as the microcanonical, canonical, and grand canonical ensembles, provide a framework for describing the probability distribution of particles among different states. Probability distributions become the characters in the statistical tale, embodying the likelihood of observing a particular configuration. Statistical entropy. The narrative deepens with the introduction of statistical entropy, a measure of the microscopic disorder or uncertainty within a system. Entropy becomes a key player in connecting statistical mechanics to thermodynamics, reflecting the tendency of systems to evolve toward states with higher entropy. The second law of thermodynamics emerges as a statistical principle, stating that the entropy of an isolated system tends to increase over time. Boltzmann's statistical mechanics. Statistical mechanics unfolds with the contributions of Ludwig Boltzmann, who played a pivotal role in establishing the statistical foundations of thermodynamics. Boltzmann's entropy formula equals Ln S equals KLNW, relates entropy to the number of microscopic configurations W and the Boltzmann constant K. This formula bridges the microscopic and macroscopic worlds, providing a statistical interpretation of thermodynamic entropy. Canonical ensemble and temperature. The discipline delves into the canonical ensemble, a statistical ensemble at constant temperature, volume, and particle number. Temperature emerges as a statistical concept, reflecting the average kinetic energy of particles. The Maxwell-Boltzmann distribution characterizes the probability distribution of particle speeds in a gas at equilibrium. Quantum statistical mechanics. Statistical mechanics extends its reach to quantum systems, incorporating the principles of quantum mechanics. The density matrix formalism becomes a powerful tool in quantum statistical mechanics, describing the statistical state of a quantum system. Quantum statistics, including Bose-Einstein and Fermi-Dirac statistics, characterize the behavior of particles with integer and half-integer spins, respectively. Fluctuations and fluctuation dissipation theorem. In the statistical tapestry, statistical mechanics explores fluctuations, random deviations from the average behavior of a system. The fluctuation dissipation theorem establishes a connection between fluctuations and response functions, revealing the interplay between random fluctuations and the system's dynamic response. Applications in condensed matter physics. Statistical mechanics finds rich applications in condensed matter physics, where the collective behavior of atoms and molecules in solids and liquids is governed by statistical principles. The study of phase transitions, critical phenomena, and the behavior of materials at different temperature and pressure conditions falls within the realm of statistical mechanics. Statistical thermodynamics. The narrative unfolds with the integration of statistical mechanics and thermodynamics into a unified framework known as statistical thermodynamics. This synthesis connects the microscopic details of particle interactions with macroscopic thermodynamic properties, providing a comprehensive understanding of equilibrium and non-equilibrium systems. Irreversibility and the arrow of time. Statistical mechanics contributes to the understanding of irreversibility and the arrow of time. The increase in entropy, driven by statistical considerations, aligns with the direction of time's arrow. The statistical approach sheds light on why certain processes are more likely to occur in one direction than in the reverse. Applications in astrophysics and cosmology. In the cosmic panorama, statistical mechanics extends its influence to astrophysics and cosmology. The statistical behavior of particles in astrophysical environments, such as stellar interiors and the early universe, contributes to the understanding of cosmic structures, evolution, and the cosmic microwave background. Quantum field theory and statistical physics. Statistical mechanics intertwines with quantum field theory, providing a statistical description of quantum fields. In the realm of high-energy physics, the statistical behavior of particles in extreme conditions, such as those encountered in the early universe or high-energy collisions, is explored through the lens of statistical physics. In essence, statistical mechanics is the storyteller of probability in the microscopic realm, a discipline that, through the lens of ensembles, entropy, and probability distributions, unravels the statistical principles that underlie the emergence of macroscopic properties. It is the discipline that, in the vast landscape of physical systems, guides the exploration of statistical regularities and fluctuations in the intricate dance of particles. In the grand narrative of statistical physics, statistical mechanics stands as the eloquent narrator, revealing the statistical symphony that orchestrates the behavior of matter across scales and epochs.